Hello and welcome, Mindsetters. You have just tuned in to Learn Extra Live Mathematics with Natasha. How are you, Natasha?
I'm good, thanks. Nice to be back at Leho.
It is great to be back. How are you on this sunny Monday?
I am feeling very good and very, very warm.
Okay. I know, it's fantastic. I love the heat more than the cold, so I'm enjoying this summer. Today we're doing probability, hey?
That's right, Leho. Guys, grade 10s, we are going to be looking at probability. It is all about the theory of chance, really. We're talking about chance and games and all sorts of nice things, so it's a nice section, that.
Awesome. Thank you, Natasha. You can go prepare your
Thank
probability board. So, guys, of course, because it's Monday, we have such awesome prizes in the studio today. As you can see, this Casio camera is up for grabs. So make sure that you are the best and greatest mindset on the page. We also have the calculator and we have the labeler. So today you have to go all out for these ones because they are up for your grabs and we are here for you. So these things are not going to go back into the back just so that they can gather dust. They are for you to come up and get them. So make sure that you're on the page. Facebook.com/LearnExtra is where we are at. And our Twitter handle is @LearnExtra, guys. Today, because it's sunny, I want you guys to tell me how your weekend went. I love hearing about weekends. If you're studying, if you were swimming, if you were out at the mall, let me know what's up, guys. I'd love to hear. Over to you, Natasha.
Hi, grade 10s, and today, as I said earlier, we are going to be looking at probability. Probability is a really interesting subject. Now, if you think over the weekend, I mean, there was so much of sport going on, so whether it's rugby, cricket, soccer, whatever it is you were watching, you didn't really know whether your favorite team was going to win or not. You sort of hoped and prayed and held thumbs and whatever else you can do, but you don't know if they're going to win. So there's a bit of uncertainty involved with whether your favorite team will win or not. Okay, although maybe not so much in the case of the All Blacks, which seem to be unbeatable at this stage. But anyway, there's always uncertainty, and uncertainty presents itself in different situations every single day. So the whole section of probability is really dealing with everyday decisions where there's uncertainty. So probability describes uncertain events. Now, there's certain terminology that you guys need to go over and you need to remember in order to do the section on probability. So we're first going to have a look at that terminology. All right. The first thing we're going to look at is an experiment. An experiment is really just an uncertain process. So for example, and I'll show you with a little example a little bit later on, but an experiment could be, for example, tossing a coin. Okay, that would be an experiment. You don't know what's going to happen. It could end up heads or tails. So tossing a coin is an example of an experiment. An outcome of an experiment is a single result of that experiment. So for example, if you toss the coin, it could come up heads. All right, so that's one of the outcomes of the experiment. The other outcome, of course, could be that it could come up tails. A sample space is the set of all possible outcomes of an experiment. So all possible outcomes, that is your sample space. So for example, if you toss a coin, it come up head, it could heads or tails. We ignore the fact that it could perhaps lie on the edge or anything funny like that, but your sample space will be made up of all your possible outcomes, which in this case, if you toss a coin, would be heads or tails. And we denote the size of the sample space by N of S, NS in brackets like that. An event is a specific set of outcomes of an experiment that you are interested in. All right, so it's denoted with the letter E, and the number of outcomes in the event is denoted in brackets E. So an event, you can also think of it as your favorable outcome. All right, let's have a look at an example. So as I said when we started, an experiment could be, for example, tossing a coin. All right, it could either land heads, H for heads, or T for tails. It could land either way. So the possible outcome of tossing a coin is that one of the possible outcomes is that it could land with its heads facing up, as in the diagram. Now, since a coin can land in only one of two ways, all right, so we're ignoring anything like, for example, it landing on its edge or anything like that, the sample space is the set of your possible outcomes. So it could end up being heads or it could end up being tails. So that is your sample space, and that's your set of possible outcomes. The size of the sample space in the case of the coin, well, how many outcomes do you have? It can either land heads or tails. So therefore, the size of your sample space is 2. There's 2 possible outcomes in this space. And let's say, for example, that we would like the coin to land heads up. Here the event, remember we spoke about the event being E. It contains a single outcome that we are interested in, which is the fact that we want the coin to land heads up. All right, so your event will be heads, and the favorable outcome here is just equal to 1 because there's only one head on a coin. All right, so if you think about it, it can either end up heads or tails, but the favorable outcome that you are interested in, or the event that you are interested in, is it landing heads up, and the only possibility here is there's only one face with heads, so therefore your event is 1, your favorable event. Okay, we're also going to carry on and look at what a probability is. So a probability is really a real number between 0 and 1 that describes how likely it is that an event will occur. Remember what we said about an event? An event, you're looking at your possible favorable outcome. So for example, you were looking at the coin landing heads up. That was an event. All right? And it can also be described as a percentage. Very often you'll see people will say things like there's a 50% chance of it raining today, or whatever the case is. All right, so percentages are often linked to probabilities, and when we talk about a probability of something or the chance of something happening, we generally go to percentages, but you can also list it as fractions. A probability of 0 means that an event will never occur. Okay, so if you think about something that will never ever occur and has a probability of 0. So for example, if you think about a 6-sided dice, you know it's all numbered 1 to 6. The probability of it ending up with a 7 on the dice is impossible because it only goes up to number 6. So therefore, that probability would be 0. And then a probability of 1 means that the event will always occur. So for example, the sun rising every day. It's something that happens all the time. So therefore, it's a guarantee. It's 100%. Okay. When all the outcomes of an activity are equally likely to happen, you can calculate the probability of an event by using this formula. All right, and I'm just going to highlight this formula for you. Okay, the probability of an event E is the number of favorable outcomes, so that's the numerator, the number of favorable outcomes divided by the number of possible outcomes. Okay, so let's go over it again. The probability of an event E is the number of favorable outcomes divided by the number of possible outcomes. So if we think about in the case with our coin, we were interested in getting a heads, right? We knew that the number of possible outcomes, it was heads or tails, so the number of possible outcomes was 2. And the number of favorable outcomes, what we were interested in, which was the fact that it ends up with a heads, that was just 1. Okay, because they could only be a heads or a tails. You can't have both at the same time. So therefore, the probability of getting a head on the toss of a coin would be your number of favorable outcomes, which is 1, divided by the number of possible outcomes, which is 2. So the probability of getting a head on the toss of a coin, which is equal to a half, which we can write as 50%. Okay. All right, guys, so that's quite a lot of terminology for you to take in. You've got to remember things like outcomes, events, and probabilities and all of this. And we're going to look at a few more examples to give you an idea of what we are talking about. But I want to quickly check with Katlego and see if you have any questions on the theory that we've done so far.
There are no questions yet, but I'm urging you guys to send through questions because we will be going through anything that you need through from the beginning of this lesson to the very end. So make sure that you jump on the page and join us. And thank you to Liberty also for letting us have this awesome show.
Okay, great. Okay, guys, so I hope that you're all understanding so far. If you have no questions, usually means that you are understanding. We're going to look at a quick example just to explain to you the formula we were using just now, which is the number of favorable outcomes over the number of possible outcomes to work out the probability of an event. Okay, so we've got a bag which contains 6 red, 3 blue, 2 green, and 1 white balls. All right, a ball is picked at random, and then you're asked to determine the probability that it's red, blue or white, and then not green. Okay, so you can imagine you dip your hand into a bag and you've got this bag full of, okay, so you can imagine, let's just say that's a bag. All right, so you dip your hand into the bag and you can either pull out a red or a blue or a green or a white ball. Okay, so in total, before we actually look at the question, let's look at the sample space. We've got 6 red, 3 blue, 2 green, and 1 white. So therefore, in total, the number of possible things that could happen when you put your hand into the bag, you could get one of the red balls, but there's 6 altogether, right? So therefore, our sample space is going to be 6 plus 3, which is the number of blue, plus 2, which is the number of green, plus 1, which is the number of white. All right, and all together that gives us 6 plus 3 is 9, 9 plus 1 is 10, plus 2 is 12. So therefore, our sample space, or the set of possible outcomes, is 12. So that's really just telling you how many balls there are in this bag. Okay, so we know there are 12 balls, but we want to know what is the probability that you pick out. So you put your hand into the bag and you pick out a red ball. Okay, now remember there's 6 possible ways to pick out this red ball. There's 6 different red balls, right? So therefore, let's look at A. We know that N of S, our possible outcomes, is 12, right? But the one that we are interested in, the favorable one, and what I'm going to do is I'm going to call it R for red, okay? So the number of red balls, or the number of favorable outcomes, because remember, we want a red ball. So the number of ways we could get a red ball is 6. Okay, so the number of red balls in the bag is 6. We know that our sample space is 12. So therefore, the probability of getting a red ball, remember the R stands for red ball, is going to be equal to the number of favorable outcomes divided by the number of possible outcomes. So it's going to be the number of red balls in the bag, which is 6, divided by all the balls in the bag, which is 12. And that gives us 6 over 12. We can write it as a fraction, as a half, or 50%. So there's a 50% chance that when you put your hand into the bag, you're going to grab a red ball. And it makes sense because exactly if there are 12 balls in the bag and exactly half of them are red, then there's obviously a 50% chance that you're going to pull out a red ball. All right, the next one says, determine the probability that the ball is blue or white. Okay, so now there's 2 different ways we can have success here. If we pull out a blue ball, then we're happy, or if we pull out a white ball. So the number of, remember your sample space is still the same. We've still got 12 balls in the bag. That hasn't changed. Okay, so we're looking now at the number of white balls and then the number of blue balls. All right, and if you look at the question, they said to you, there are 3 blue and 1 white. So therefore, the number of whites is equal to 1 and the number of blue balls is going to be 3. Okay, So 3 blue and 1 white. So there's really 4 different ways that you could be successful in this specific experiment. If you put your hand in, if you get a white ball, you're happy, or if you get a blue one, then you're still happy. So therefore, if I want to work out the probability of getting a blue or a white ball, it's going to be the sum of these. So remember, there's 4 different ways that you can be successful here. So therefore, the probability of getting a white or a blue is going to be equal to the number of favorable outcomes, which is going to be 1, okay, because there's 1 white ball, plus 3, because there's 3 blues, all over the number of possible outcomes, which is 12. So therefore we get 4 over 12, which is a third, or if you want to write it in decimal form, it's 33,3 recurring percent. Okay, so there's a 33% chance of getting either a blue or a white ball. Okay. So far we've looked at just using that basic probability formula where the probability of an event occurring is the number of favorable events divided by the number of possible, the number of favorable outcomes divided by the number of possible outcomes. And that we use to help us work out the probability of drawing a specific color from this bag. Okay, and then the last question says, determine the probability that the ball you draw out the bag is not green. Okay, so it's not green. Now, if you have a look, we've got 6 red, 3 blue, 2 green, and 1 white. So therefore, the number of balls that are not green, well, if we've got 2 green balls, okay, then the number that are not green, because remember there's 12 balls all together, so therefore the number of balls that are not green is going to be 12 minus 2, which is 10. Okay, so that takes care of all the other colors in the bag. So there are 10 balls in the bag that are not green. So therefore, the probability of getting a ball that is another color, so we'll say another color other than green, is going to be 10, which is the number of favorable events, divided by your sample space, which is still 12. And that we can simplify. We can say 2 goes into 10 5 times, and 2 goes into 12 6 times. All right, guys, so what we call this, where the event where you get something that's not green, for example, we call that a complementary event. There is another way we could have worked this out, all right, but we're not going to delve into that right now in the beginning of this lesson. We might get to that a little bit later on. But this probability of getting something that's not something else, so not green or not blue or not white or whatever you want to say, that is called a complementary event, when we say 1 minus the probability of something else happening. But as I said, we're not going to get into that straight away right in the beginning of the show. We'll get to that maybe a little bit later on. All right, I think it's a good place to take a break.
Yes, I think it is. So guys, we're going to take a really quick break for you guys, maybe to get a cold glass of water before joining us again for the next segment. See you just now. Welcome back, Mindsetters. If you have just joined us, we are doing grade 10 mathematics, and today we're focusing on probability. So please send through any questions that you may have with regards to probability, because we're very keen to answer them. Also, another thing that I've said, tell me how your weekends were, guys. It's been so nice and hot, so I want to know what you guys got up to as well. Over to you, Natasha.
All right. Okay, guys. So I've had a look at the Facebook page, and I see some of you maybe missed our first section where we went over the theory, and you're asking questions like, what's the difference between outcomes and events? Remember, we did this right at the beginning. We discussed what an outcome is and what an event is. For those of you who missed that, let's quickly go over it again. An outcome of an experiment is a single result of that experiment. So the example I used is that if you toss a coin, a possible outcome is heads, another possible outcome is tails. So if you toss a coin, there's two things that could happen. You can either get heads or you can get tails. The heads or the tails, those are called outcomes of the experiment. Okay, so that is what an outcome of an experiment. It's a single result from that experiment. The sample space is the set of all possible outcomes. So therefore the sample space in this case, if we toss a coin, will be heads or tails. That's the complete, those are all the possible things that could happen if you toss a coin. You can either get heads or tails, so that is the sample space, your set of possible outcomes. All right, so remember an outcome is a single result. Okay, so for example, heads is a single result and tails is a single result. So those are outcomes of the experiments, and together, if we combine them, the sample space of an experiment is the set of all possible outcomes. And another thing that some of you were asking is what an event is. An event is a specific set of outcomes of an experiment that you are interested in. So for example, if you think about an event where you've tossed a coin and you are interested in the fact that you would like it to turn up heads, then the event that you are interested in is heads. So therefore the event will be your favorable outcome, which is the tossing of the coin, and then it must end up on the heads side. Okay, so heads would be your favorable outcome. Okay, so your event is really just your favorable outcome that you are interested in. Okay, we're going to carry on with a little bit of theory and something that a lot of people seem to get confused with, and this is unions and intersections. Now, the union of two sets is a new set that contains all the elements that are in at least one of the two sets. Okay, so a union, let's go through it again. A union of two sets is a new set that contains all, very important, it contains all of the elements that are in at least one of the two sets. We denote the union as A union B, so the symbol we use for union is A union B, and that denotes all the elements that are at least in one of the two sets. Okay, so that's what a union is. The intersection, and I'll show you with diagrams as well what a union is. The intersection of two sets is a new set that contains all the elements that are in both sets. Okay, so the intersection is really combining everything that's common to two sets. We denote the intersection with this sort of upside down N as A intersection B. Okay, so the intersection of two sets is a new set and it contains all the elements that are in both sets. Okay, now if we have a look at some of these Venn diagrams, remember a Venn diagram is just used to represent elements in a set, and we can use these round circles to represent different elements in a set. So it's contained in this round, in these round rings, and we put our numbers in, and those are our sets. And the S outside the little square, that's called your sample space. So it denotes all the elements inside A and B. Okay, now in the middle column, so if we're looking at this one, okay, that's the one we're looking at. So in that middle column, what you will notice is that the intersection, A intersection B, is empty. Now remember, intersection is something that will contain all the elements that are common to both A and B. But if you look at these two sets, we say they are disjoint. There's nothing common between these two sets. All right? So for example, if you think about all the prime numbers that are even and all the prime numbers that are odd, okay, even and odd numbers are not going to have an intersection. They're two completely different sets. So their intersection would be 0. Okay, so in the middle column, we can see that the intersection is 0 or empty since the two sets do not overlap. Okay, And then if we look at this last column here, so what you'll see in this sample space is that your set B is completely contained within the set A. All right, so the union A union B is equal to everything that's in A, because remember, whatever's in B is already in A. So therefore A union B is just going to be the entire set A. Okay, and if you look at the intersection, which is where they overlap, you see that B is completely contained within A. So therefore A intersection B will be just your set in the middle, so just that B. All right. Okay, so let's just close that off. Right, so A intersection B in the last part was equal to B, since B was fully contained in A. And what this all leads us to is the theory of probability, and where we get to this idea of the probability identity. Okay, so if you're looking at the probability of A union B, so the probability of A union B, so we're looking at the probability of two different sets, okay, and we're taking the union of those sets. So probability of A and the union with the probability of B. Now, if you just add all together and you say, okay, well, the probability of A union B, so for example, if we look at the first diagram, if we said the probability of the two is just going to be the probability of A, whoopsie, the probability of A plus the probability of B. If we just do that, without taking into regard this intersection between the two, you're going to overcount elements, because you're going to count elements in A that are also common to B, and the elements in B that are common to A. So therefore you can't just say that the probability of A or B is the probability of A plus the probability of B. We have this little identity that you have to use. Okay, so the probability of A union B, so that means probability of A or B, is equal to the probability of A plus the probability of B minus the intersection of A and B. So minus the probability of A intersection B, and that's very important. As I said, if you leave that out, you're going to be, and the two sets happen to intersect, then you're going to be overcounting. You're going to be taking elements from A that are in B and elements from B that are in A. So you have to have this identity to work out the probability of a union of two sets. All right? However, sometimes you get sets or events that are mutually exclusive. So think about things that are mutually exclusive. So for example, sleeping and eating. Right? Those are mutually exclusive. They cannot happen at the same time. If you're sleeping, you cannot be eating. And if you're eating, you generally are wide awake. Otherwise, there's a serious problem.
Or you can be a sleepwalker.
So excluding the sleepwalking possibility, eating and sleeping are mutually exclusive. So these are events that cannot occur at the same time. So then we say they are mutually exclusive. So whenever an outcome of an experiment is in the first event, it cannot also be in the second event, and vice versa. So therefore the intersection, so what we were saying, eating and sleeping, the intersection, the probability of it happening at the same time is 0. Then those events are called mutually exclusive. Then we can use the identity that the probability of A union B is equal to the probability of A plus the probability of B. So it's important that we just pick up this point now. Okay, so there's two different identities that we looked at. We looked at the probability of A union B when A and B intersect. So for example, we were looking at something like the very first square there, the very first sample space. If they intersect each other, then the identity you will use to work out the probability of the union is this one, where you subtract the intersection out. However, if they do not overlap, so they are mutually exclusive, so like in the second diagram, these are mutually exclusive. Okay, whatever is happening in A is not also happening in B. If these two are mutually exclusive, then you can say the probability of A union B is equal to the probability of A plus the probability of B, and that's only if we're looking at finding the probability of the union. Okay, and the reason we can use it there, and we don't have to exclude the intersection, because the intersection in this case would be naught. So when you're dealing with mutually exclusive events, what I'm stressing here, it's important to note there are two different identities. Mutually exclusive, the probability of the union is just the sum of each of the probabilities, whereas if the sets are not mutually exclusive and they intersect each other, then the probability of the union is the sum of the probabilities minus the intersection of the probabilities. So it's quite a lot of theory to take in before we do an example based on this whole concept of Venn diagrams and mutually exclusive and that kind of thing. So I think this might be a good place to cross back over to you, Katlego, and perhaps take a quick break.
Okay, let's do that. So guys, we're going to take a really quick break. In this break, as I always say, please send through every question that you need to send, guys, because that is exactly what we're here for. See you just now. Welcome back, Mindsetters. This grade 10 show has been so fantastic, and many of you on the page have been saying that you've really enjoyed learning about probability, or you're enjoying probability, or that you're understanding probability so much more now that we've done it. I'm so glad to hear that, guys, because that is exactly what we're here for. Now, if you have any questions whatsoever on probability grade 10s, please send them through, guys, because this is actually the second last maths lesson. Hey, Natasha.
That is
so
correct.
It's time
Very
that
sad.
you guys get this section actually up to scratch, because it's so important. And it's such easy marks for you guys to just get into the bag and pass really well. Over to you.
All right. So some of you are asking questions on things we've already done. So I'm not sure if you just didn't tune in on time or what the case is. So I'm going to go over unions and intersections very briefly, just simply because we need this concept of a Venn diagram in the next question I'm going to do. So the union of two sets, we said, is a new set that contains all of the elements that are in at least one of the two sets. So for example, A union B would be all of that plus all of that. Whatever's in A plus all of B would give me A union B. Obviously, you will not repeat elements that are in the intersection. Okay, so A union B, that's an idea of A union B, and the intersection is just where the two sets, obviously, as it says, intersect. So wherever they have something in common. All right, so I'm just trying to undo that. There we go. So wherever these two intersect, so that little orange part that I'm shading in there, that we denote as A intersection B. It's a completely new set, and it always contains things that are in both set A and in set B. So intersection you can think of as an and a union you can think of as an or. Okay, so it's A or B gives you your union, and A and B gives you your intersection. All right. Okay, remember Venn diagram we use to list all the elements in a set. And I think, guys, that if you are having a bit of a problem with this union and intersection business, we're going to do a question now, and it will hopefully make things a little bit easier. All right. So we are told that customers at a shop were asked if they had bought milk, meat, or both. 150 people were questioned, and the answers were, and they tell you 125 people bought milk, 85 bought meat, 70 bought both. Okay, so this is an experiment that took place. People were questioned about whether they bought milk or meat or both. And then there's a whole lot of questions that we are asked about that. We want to know how many people bought neither milk nor meat. Okay, so what we're going to do is let's just set up a little bit of a set going, okay, because bought milk, bought meat, we can't really state things in that way. So what we're going to say is let the number of people Now I'm just going to work at the bottom here. So if you bought, the number of people who bought meat, we're going to call that set A. All right. And then the number of people who bought milk, we're going to call that set B. Okay, it's just going to make it easier to label them with A's and B's instead of bought meat, bought milk all the time. All right. So we've got 150 people that were questioned, and the answers were, they said 125 bought milk. Okay, so the number of people that bought milk, so N of set A, okay, well I'm saying N of A and I'm saying milk, but A is actually meat. So the number of people who bought meat was 85. And then the number of people that bought milk was 125. And then they tell you on the side that 70 people bought both. So the intersection, the number of people that bought both, so the intersection of A and B is 70. So 70 people bought both milk and meat. So therefore, the intersection of A and B is 70. All right, now let's use all of this and see how we go about answering the first question. So here they want to know how many bought neither milk nor meat. Now, if you think about it, if you had the number of people who bought either milk or meat, right, if you had that total number, then if you could say 1 minus that total number, then you will get the number of people who bought neither. Okay, so let me go through that again. So if you can work out the number of people that bought either milk or meat, so the union of those two, then if I wanted to work out how many people bought neither, neither being the negative, neither milk nor meat, then all I've got to do is take the complement. Remember the complement we said at the beginning was 1 minus whatever we were interested in. All right, so if I'm looking at the complement here, how many bought neither milk nor meat, I first need to work out how many bought either milk or meat. Okay, so if I can work out how many bought milk or meat, and then I say 1 minus that, I will know how many bought neither. Okay, so we need to work out NA union B. Remember, we're going to use that identity. So we're looking at the number of people who bought either milk or meat. It's going to be the number who bought meat plus the number who bought milk minus the intersection, so the number who bought both. Okay, all right, so that's the identity that comes straight from your probability identity. So therefore, the number of people who bought meat we had was 85. The number of people who bought milk, 125, minus the number of people who bought both, and that was 70. Remember, guys, here I just have to stress, at this stage we're not doing probabilities. They just want to know the number of people. So we're not going to say 85 over 150 plus 125 over 150 minus 70 over 150. No, because we're not interested in the probabilities. We're just looking at the number of something. Okay, so that's important. We're using the same identity, but we're not using the probability of the number of people who bought either milk or meat. We're using just the number. Okay, we're not interested in the probability at this stage. So therefore, if I work this out on my calculator, I'm going to have 85 plus 125 minus 70, and that gives me 140. So therefore, we're saying that 140 people either bought milk or they bought meat. Okay, 140 people either bought milk or meat. But remember, that's not what the question asked. The question said, how many people bought neither milk nor meat? So it really is just the complement of this event, of this number. Okay, so we know that there is 150 people in total. Okay, if 140 bought either milk or meat, then it means that 150 minus 140, which is 10 people bought neither milk nor meat. Okay. All right, so let's just go through this again, because I think when you first start dealing with these probability identities and that, it can be a little bit confusing. Okay, so let's just go over it again. We first worked out the number of people that bought either milk or meat, right? And that gave us 140 people. Once we got that 140 people, if 150 people in total were questioned and 140 either bought milk or meat, that means the remaining 10 bought neither milk nor meat. So therefore, for the first question, our answer is 10 people. 10 people bought neither milk nor meat. All right, I hope that's clear, and if not, please do post your questions on the page. All right, so now we're going into drawing of a Venn diagram to illustrate the information. All right, so let's have a look. Now remember, the Venn diagram is just going to show your sets. It's going to show you what's in A, what's in B, what's the union, what's the intersection, and all of that. All right, so we start by saying we'll draw a little square to represent our sample space. Sample space, remember, contains everything that's happening. All right, and then we're going to have two sets. We're going to have, and I'm going to use two different colors. We're going to have A, and then we're going to have, okay, I said two different colors, and then I use the same one. So let's just get rid of that and start again. So we're going to have A in blue, and then we'll use pink for the other one. All right. So this is A, and this is B. Okay, so let's have a look at what's happening. We've got 70 people in the intersection. I'm going to start with the intersection because it's the easiest to put down. 70 people bought both. All right, so 70 people bought both milk and meat. Okay, so here A is meat, B is milk. So 70 people are in that little intersection. 70 people bought both. Now remember, they said to us that 125, okay, let's go back to the information, 125 bought milk. But 70 of those 125 also bought meat. So therefore, if I want to know what's just in set B, I've got to say 125 minus 70, and that's going to give me 55. So those are the number of people who only bought milk. So 55 people bought only milk, 70 bought both meat and milk. All right, then they told you that 85 people bought just bought meat. So therefore, remember also we know that 70 of those would have bought meat and milk. So we need to take away that intersection. So 85 minus 70 will give me 15. So therefore 15 people bought only meat. Okay, so let's go through it again. 70 people in the middle, represented by the intersection, bought both milk and meat. Okay, We were also told that 125 people bought milk. So therefore, if 125 people in total bought milk, if I say 125 minus the intersection of 70, I get 55 people who bought milk only. Okay, in a similar way, we know that 70 people bought both milk and meat, but 85 people altogether bought meat. Then 85 minus the intersection of 70 gives me 15, and that means only 15 people bought meat. All right, so if you have a look at the numbers, if you add all of this up, 15, 70, and 55. In fact, let's do it and see what you get. Okay, so if I take the number who bought meat, add it to the intersection, and then add it to the number who bought milk, I get 140. And what do you notice? There's 10 that's not accounted for. Okay, because remember, there were 150 people in total. So this entire sample space contained 150 people. So there are 10 that are not catered for in that union. So therefore, those 10 are the ones we worked out who bought neither. Those 10 will sit on the outside of the two sets. All right, so that's how we represent our entire sample space and Venn diagram for this question. Okay, if you add everything in the sample space together, you must get back to your total sample space, which in this case is 150. All right, I'm going to wait a little while for all of that to sink in and just check over with Katlego to see if there's any questions on what we've just done.
You know what? There aren't any questions right now because I feel like you've gone through everything that you have, except that Dipolelo has something. I don't know if you've gone through it. What is relative frequency?
All right, I think what we're going to do with that, that's, you know, you can either get relative frequency or theoretical probabilities. I think that's a section that needs to be discussed in detail in next week's lesson because we are doing 2 shows on probability and we can't fit in everything in today's show. Like some of you are asking for independent events and all of that. Unfortunately, we can only fit so much in an hour.
Yeah.
So I'm going to leave the teacher to next week to discuss relative frequencies and independent events and all of that. But basically, there's just 2 different ways you can work out your probabilities. You can either do it based on theory, or you can do it by trial, by actually like doing the experiments. Okay, so those are the 2 different ways you can work out probabilities. We are today just looking at the theoretical approach. All right.
And Nsako asks, what is a two-way diagram? Are you going to go through that next week or the teacher next week?
Well, today we're just looking at our Venn diagrams and all of that. I'm not sure what he's meaning with a two-way diagram.
Hey? Okay.
I'm not too sure what he's
Just
asking
maybe you can
there.
clarify that for us and we will try answer that.
All right. Okay, so if there's nothing relating to this question, can we carry on?
Yes, we can.
All right. Okay, guys, so let's carry on with our Venn diagram and our sample space. So we've listed everything that's happening in this specific experiment within the sample space. All right. Now, let's see if we're ready to answer question C. So now we're doing probabilities. Remember, the first 2 parts we were just looking at the number of people. Now they say, what is the probability that a randomly chosen customer firstly bought meat but no milk? So we want the probability that they bought meat, but then they must have bought no milk. All right, so let's have a look at that. So we want the probability that this person bought meat, which we represent as A, and then they bought no, so a union with no milk. Is that right? Did they say meat and no milk or milk and no meat? I'm getting all confused. Bought meat but no milk. So we want the probability that they bought A, but then none of B. Okay, so union, and because I don't want to introduce complementary symbols and that, I'm just going to take that out and say none of B. and no milk. Okay, so meat but no milk. So we know if we have a look how many people, and this is where our diagram is very, very useful. Look at your diagram. We know that 70 people bought both, 55 bought milk only. So how many bought only meat? It's only what's in A. So it's going to be 15 over the total number of people which were questioned, which is 150. So therefore, you can work out your probability. 15 divided by 150, and you get 1 over 10, which is also equal to 10%. Remember, guys, if you want to work out percentages, you just times by 100 over 1. All right, and I am quickly running out of time, so I'm going to just try and get to the last part. So there's 10% of people who bought only meat. And then the last part quickly, neither meat nor milk, just straight from your diagram. Only 10 people bought neither meat nor milk. So therefore it would be 10 over 150 will give you the number of people that bought neither. All right, so that was a quick jam session of probability. I hope that you guys enjoyed that and you understood all that we've done.
Thank you, Natasha. Thank you, Mindsetters, for such an awesome, awesome show. Thank you to Liberty as well for bringing us this show. Remember that there is some interaction you can do on the page. There's a study group. There's still the chat. You guys can still talk to each other and ask questions, guys, because it's so important. You guys are all in the same boat right now, so you all need to get help, and the best way is to help each other. Thank you from me for such an awesome show. See you next time for some more maths. Bye, guys.